Thank you for everybody for coming. I think, Brent, you want to introduce us? Give us a quick introduction?
Sure. Well, thank you, Wilson, for speaking at our October meeting of the Edmonton Data Professionals, formerly known as PASS Group. And thank you all for attending. We're just discussing what to do for November and future sessions. So if anybody has something they want to talk about or suggestions, that would be great. Without any further ado, let's pass it over to you.
Today, welcome to the presentation today. So today we're going to dive into a practical guide to PySpark in Azure Synapse Analytics. One of the things we talked about last sessions where we kind of fly through the Spark piece really quickly, and in this session we're going to dive a little more into how Spark works, the fundamentals, the architecture, and as well as how we can use Synapse effectively. So before we dive deep into the contents there, a quick introduction about myself. So my name is Wilson Mock. I have over 20 years experience in IT. Started my career as a software developer. I'm currently consulting at SMS Equipment as a data architect as well as a technical lead. Previously, I worked at a company like Avanon as a manager of data engineering, lead data architect at CAE, as well as lead AI architect at Air Canada. So I'm also a Microsoft Data Platform MVP and a Databricks champion. So if you'd like to follow me, I can be found on LinkedIn, GitHub, and a YouTube channel that I just created recently to post the recordings that we have here. I also have a Twitter handle that I will start using soon that Chris got me to set up. I just haven't had a chance to get that all completed. But yeah, that's a bit about me. Great. So kind of talk quickly about what we going to cover today, but diving a little more deeper into that, we definitely going to talk about the architecture side of things, about Spark and how it handles large and complex data set. More importantly, also how Synapse implemented Spark. There's some changes that they made as well, the enhancements, and we want to cover the differences that they have. Dive into some of the common challenges that we see when people start using Spark. Things like data partitioning, data skewing. Some stuff are very common across even in the SQL Server query space, but it's slightly different in terms of how the problem need to be troubleshooted and identified. And then we're going to jump into the demo. We only have one demo today that will cover majority of our some of the challenges that we see and some of the basic command that I can spend a little more time going in depth on, and as well as talk about how to use Spark UI to do troubleshooting, that detecting some of the data skew or the partition issues that we might see. So for the audience here, having SQL or Python knowledge is definitely beneficial. Some of the component might be on the more complex side would be challenging if you don't have either one of them, but for the most part, for the presentation should be okay with that, with just basic knowledge there. We will also do a quick 5 minutes Q&A before the demo. There's quite a bit of deep technical stuff that we want to go over and just don't want to overwhelm everyone. So we'll do a quick break between Q&A to answer any questions before we dive into the demo, and then a longer Q&A sessions right at the end there. All the code that you will see today will be accessible by in my GitHub repository as well. So the link will be available at the end of the presentation. A bit of catching up from our last session. So last sessions we focused on talking about data analysis using serverless SQL and serverless Spark, and we dive quite quickly through all the technical type of data analysis that we had to do. So you can also scan that QR code to get to the YouTube channel where this session was recorded, or there's a few items in my playlist that you can look through as well. Back to what is Synapse. So we covered quite a bit of that in our last introduction. So there's two main components here. There is the data integration piece, which is the data pipeline, orchestration, monitoring, it's very similar to Azure Data Factory, how we can bring data into Synapse and then schedule and process those data. That more fall under the integration piece. And then for the analytic runtime, last time we dived more deeper, I would say, into the SQL side. And today we'll focus primarily around the Apache Spark side. Okay, and if there's any other topic you guys are interested in future sessions, let me know. We can definitely arrange those with Brent and Chris and Theus as well. Okay, so diving straight into the Spark architecture. So at a high level, Spark is a distributed system designed to handle data processing in memory. So what that really translates to is work is going to be done using multiple machines. Done in the memory, majority of the time will be in RAM if possible. And that allows the data to be processed much faster than traditionally if you're dealing with data being written into a storage account or in a disk. And the other benefit is with multiple machines, you're enabling the ability to do parallel calculations at the same time. So you can calculate one part of the data set in one worker and then another data set in another worker. And we'll dive right into what the worker really is. In Spark, the whole driver, worker, the master-slave or the parent-child relationship there, everything is run on something called cluster. So that basically means your workload, your application runs inside this set of machines, and they're running in isolations from any other clusters that you have, regardless if the machine is being shared or not. Okay, it's very similar to like your SQL Server. You have a cluster of machines being run on. Pretty similar concepts there. The driver, this is the brain of the cluster. The goal is to ensure that the data is being distributed and the calculations being done by the workers in a timely fashion. And that's really all being done through what they call Spark context. He's like a good analogy to think of it is like the head chef, right, in a kitchen. So the head chef doesn't often do the cooking. They tell all the other cooks that they have to cook the meal and make sure all the meals are being cooked at the same time for the table, so you don't have people eating 20 minutes before the next person get their meal, essentially. Now, the worker itself on the right, that is basically the cooking station. The executor is the cook. So the cook will cook the meal, it will execute the task, is what the driver tells them to do. In the Apache Spark, you usually have a one executor per worker model. So it's a one-to-one relationship. Now, not every vendor does that. In Databricks case, you can have usually two executor per worker, just a different type of optimizations that they do and how they implement this Spark architecture there. Now, in the middle, we have something called a cluster manager. And essentially, the job of that is make sure there are the worker VMs available just in case if anything happens, if they die or we need to spin up new VMs, then that's the cluster manager's job to take care of those responsibilities. They want to make sure there's a cook available to cook at the cooking station. If there's no cooking station, you make sure that you set one cooking station on the fly, but that's kind of how that works. And your Spark application really is all the commands that you see in your notebook or in your Python code. Using the same analogy, that's basically your food order, right? Your table, your waiter provides you with the order for your table, what each patron has ordered. Adding a few more pieces onto the initial diagram. So following the same kind of analogy, we have the head chef looking at the order. So in this case, our upcoming job, which is under the Spark application, is to make a kebab. And the ingredients that we have, or the data that we have, is we have some chicken, we have some beef, we have some fish. The chef separates the data, the ingredients that they need, asks the executor, or the workers in this case, to make the kebab for them. So, this kebab might take 1 beef and 3 chicken. He separates them, tell them to make the kebab, and then each of the executor will go ahead and make that food. Now, in Spark terminology, the data is partitioned because it takes 3 chicken and 1 beef, and those are partitioning partially of your data. And then the dishes at the end need to be put together by one of the executors so that they can compile all the information and send it back to the user that requests them. Just one last thing we want to cover in this slide is the fact that the Spark application, like I mentioned, runs in isolation. So if you have multiple Spark application running, the cluster doesn't talk across from each other. It's just important to reiterate that. So with that understanding, let's talk about how Synapse Spark really works that enhances the experience of Apache Spark. First of all, when you work directly with Apache Spark, you need to manage your cluster quite closely. So every job you run, you need to kind of tune how your cluster needs to function. And that's quite a bit of overhead, right? When you have various different workload, different queries you try to run, you cannot really manage each cluster, which causes a lot of overhead. To help dealing with that issue, Synapse implemented auto scaling as well as Synapse Pool to help with that issue. So that's kind of the item on the left-hand side there. The Spark Pool, what it allows you to do is you can specify, I want 5 to 10 machines. And when your workload starts, you will allocate the minimum machine, which is 5. And then you will scale all the way up to 10, not as is required. More importantly, that the pool itself can service multiple applications. So you can have 2, 3, 4 clusters available inside one pool, based on the cluster definitions, of course, in this case. So yeah, so that's kind of help with scaling up and scaling down on the number of virtual machines that you have. Also, it's important to note that when you do this auto scaling, regardless you use or don't use the machine. So let's say you define your pool to be 7 machines, but you're only running 3 right now. You are paying for all 7 machines. So it's very important to correctly size the pool based on your workload and based on how your end-to-end job is going to flow with the processing that you have.
And do you pay for the pool the same rate whether they're used or not?
Correct.
Okay.
Yeah.
It's just the allocation.
You pay for the VMs that's in the pool. The definition of the pool doesn't cost you any money.
Okay.
Yeah. So it's a configuration that you say 5 to 10 machines, but when you use the pool, you pay minimum 5.
Okay.
Yeah.
So what happens if one of your VMs doesn't work?
And that would be the responsibility of the cluster manager to make sure they swap that out if the executor died. Quite rarely your VM itself won't work. It's the executor that, because the processing overloaded, it dies. And it does happen. And then the cluster manager will say, oh, you're missing a cook. Go find me a new cook.
But if you can't find one, it would have to readjust to...
Yeah, let's say if you decide to use
I'm thinking more
spot.
problem on
Yeah.
the VM. Like, you think you can use it, but you can't
Right.
because something's wrong with it.
Yeah, so let's say a spot instance is probably a more often example is Microsoft give you a VM for cheap, right? Because it's over allocated, no one's using it right now. They can take it away at any moment. So in that case, yeah, your VM is going to die along with your executor, and then it is the responsibility of the pool to go find you a new VM, right? And then the cluster manager then can bring the cook in, stand up the cook. Now, one last thing is, in Azure, standing up a virtual machine takes about approximately 3 minutes to stand up. So you really want to make sure your initial pool size is correct, or else you'll be spending a lot of time scaling up and scaling down and waiting for machines to be available to you. And usually that does go through some trial and error, as you monitor your progress during in development and things like that to make sure you get that number quite right.
Okay.
Finally, the pool, if it's idle for too long and there's nothing running on the cluster, you will automatically shut down. There's an automatic pausing configuration that you can enable, which we'll look into during the demo, or else you will always be paying for those VMs, which is not a very good thing. The next really interesting question is, if I have the pool of VMs, I still need to scale up and scale down my cluster in terms of workers. How do we go about doing that? Let's say your configuration for your cluster is 3 to 6 VMs, and you always allocate 6 VMs that you're paying for, even though you're not using. That can get expensive in a hurry, right? If you have multiple clusters. So what Synapse and Microsoft did is you implemented this thing called dynamic allocate executors. And what that really means is if you focus on the orange boxes in the pool, we really have 3 machines running right now in the cluster number 2. The machines that is grayed out in this case in the middle row, that machine is not allocated, so the pool hasn't spin up that machine at all. But that machine is actually preemptively reserved for cluster 2. So you're not paying for that machine, but the cluster know that if I give that machine away, then we're gonna have a cluster capacity issue essentially. So they hold on to that machine and say that, hey, that will be in use, do not touch for other clusters. Reserving of the virtual machines there. Yeah, and you don't have to pay, of course, because the VM is not actually up and running.
Presumably you can get reporting to know how you're using the VMs.
In the Spark UI and in the monitor tool, they tell you how many cores you're using, how many things you run. We'll dive into a little bit of those items, not in too much depth. Probably need different sessions as we move towards like the scheduling of the pipeline and things like that. We'll cover that more closely there, as we're running everything mostly through notebook, right? So it's pretty straightforward for us. It's much more challenging when you're running multiple notebooks, one after another, and there's different processing requirements. And that's when we start seeing the fluctuations of machine scaling up and down. Now, the last thing here is the intelligent cache that Microsoft has enhanced the Apache Spark. So in this feature, Synapse will try to detect frequently accessed data and put them in the cache ahead of time. So, pre-caching, pretty much just like SQL Server or even Windows machines does, right? In the kitchen example, if you're trying to cook a steak meal, right? You might have some mashed potatoes and gravies that come with your steak. You don't want your cook to be running around gathering gravy every time they need to cook your food, right? So, and that will help, with the executor speed, which give you the overall performance that Spark, is known for. So we'll take a quick Q&A here. I know I cover a lot of content and material, so I just want to give everybody on the call and as well as here a chance to ask any questions before we jump into the few more slides.
Bobby S. was wondering if the PowerPoint could be available.
Yeah, I can make that available. I usually put the sessions and then post them on the YouTube channel, so you will see all the slides again.
Awesome. So we should
Yeah, because I'm
subscribe
kind
to
of
your
new
channel.
to your YouTube video. I'm not aware of where you put your things, but that's totally okay.
Yeah, so in the YouTube, in terms of the YouTube, I usually post on the group, in the Edmonton data group once it's available. It does take me a little bit of time to edit because I got to do all that stuff myself. But once it's ready, I'll post it. Sometimes I have some fact-checking correction that needs to be made, and I make those before I make the post for them. So yeah.
Sounds good.
Okay, I have a question.
Yes, sir.
I was a SQL DBA, so what versions of SQL really support this?
It doesn't, in short, because this is all run under Apache Spark, so it's not the same technology stack. A lot of companies used to host Hornwork or Hadoop infrastructure, and is their way of hosting an on-prem Apache Spark and to manage it. And
It's
that's,
okay if I answer this?
yeah, go ahead.
We use Synapse. We have probably 20 technologies here. Synapse and Apache Spark is one of them. And we use that on probably 20, 25 databases. Probably half of them are on-prem, a lot of them in Azure. So it usually supports for a variety of SQL databases. Now, how far back of the version of the SQL, I wouldn't be able to tell you, but it's pretty straightforward how to do it on-prem.
Well, if you're in Azure, you're in the most current anyway,
Yeah.
unless you've set your compatibility level down.
Synapse is a little bit different. Like Synapse is more based on the data warehouse side of things. So they run their own parallel, like they run their own engine that's customized for that, because the parallel workload on the SQL side is also different. It's not directly based on the SQL engine. Go ahead, Bobby. You want to add anything to that?
Yeah, we use a lot of like linked services and stuff like that that is building to Synapse. Because we do a lot of ADF, Azure Data Factories as well, ADF pipelines. And we might have probably like 40, 50 Synapse ones. So we do have a lot of data going back and forth for on-prem. So it's not a...
Sorry, we lost you there, but I think what Bobby is trying to say is in the Synapse technology, through Azure Data Factory or in Synapse integration, you can extract and push data back and forth with either Azure SQL or Microsoft SQL. And that may be a future sessions we can cover. So you can do all of that. It's compatible with, I think, even 2009, maybe even back more on SQL Server. They can push the data back and forth. It just uses the ODBC, JDBC drivers. So it's pretty flexible. But in terms of Synapse accessing the data in a SQL Server or SQL Server connecting to Spark directly, that is usually, we need to create a table in Spark first, and then SSMS or something can connect to Synapse.
Unfortunately, as my experience was limited in Azure,
Yeah.
more on-prem, so you're the one who has to push it up.
Yeah.
There's a version where Azure,
They deal that for you.
they do it for you, and
Yeah.
it's like asking you about the worker threads there. When you're in Azure, you're thinking if you're on-prem, well, you've only got this physical machine, but when you're in Azure,
Right.
it's
It's-
enormous what's
yeah.
out there, and therefore it's not that difficult to reallocate. Yeah.
Yeah, even for on-premise, you probably run the virtual VMs nowadays, not on bare metal, right? So you might split up your 64-core Intel machines or AMD, and you or Threadripper, whatever you guys using, and probably allocate 32 of that to your SQL clusters, right? So very similar in that concept. The main takeaway is the data that you store. Spark likes to work on the data itself, on a file base, not so much on a query base. It can, it's just not the most ideal. Which is why Bobby is saying that you extract the data first, put it as a storage file, and then you access it. I think that's also aligned with the first demo that we had with the data analysis. We did the extraction ahead of time.
Depending on your use case, there's 100 ways to do this, to move from integrate on-prem with Azure. I know we do at least 25 ways here, but there's no one way that, like I said, it depends on your use case and what you have and what you need to send back and forth, whether you want to interact both with Azure DB and on-prem, or you want to ETL it to, or your migration, because what we're doing here, we're slowly phasing out some of our on-prem, but we're still using it at the same time. So we have a team separate that deals with that, and like that.
Right.
We have a lot of servers that are on-prem due to acquisitions and that sort of thing in other countries. So we have to. It's a very slow process where a large company has to deal with that sort of thing. But if you're a smaller company, then, like I said, some of the things may be actually easier to do. But once you get it up in the cloud, like I said, this is a pretty good tool to manage that.
Yeah, a lot of people do use Synapse nowadays.
We use it.
Yeah, that's the second generation of the data warehouse really fixes a lot of problem than the first one they first released. So it's a very common tool that people use. Okay, maybe we'll carry on. I know we only have the lunch hour here. Just have 2 more slides and we'll jump over to the demo pretty quickly there. So the next thing we really want to talk about is shuffling. And what that really means is the data needs to move between executor or workers. And that, obviously is not quick. And why would we want to do that, right? And that's based on the type of operation you want to do in Synapse. So there's 2 types of operation that we do inside Synapse that we run. Narrow operations, basically things that you can be ran inside a worker or inside a partition. You don't need to move data between any partition to do your calculations or your processing. So things like selecting, right? You can select per partition by yourself, no condition, no issues. Filter or the where clause, same thing. You can apply the where clause usually on the data itself, assuming you're not doing any aggregation or group by. When you're creating a new column with the logic that based on row level calculation. So for example, you want to find out cost per mile that you're doing. You have the mile, you have the cost, just divide them. It's all row level calculation. Or things like condition. You use the case statements in SQL, for example. When you're doing sampling, you're just trying to extract a sample set of data using from your data set, and that's quite useful when you're doing like testing or when you're putting something in production. During development, you want to make sure there's a good sample size of data that you're testing. No corner cases are going to be found, and of course things like union to set the data together. There's no they work independently, right? The more challenging part is when we start doing wide operations. And those are usually things that are when we're doing aggregations or joins. So we'll go over them kind of quickly for each one. So aggregation or sorting, so things like group by, no different than the SQL one. You're grouping data by usually a category, right, or a date. And those dates usually is not the key field that you're operating on in Spark. Or ordering data, that means you're basically resorting the data, moving the data within the partition around. And finally, when you do things like Windows function, that causes a havoc on on all the partitions, and even in SQL, that's a heavy operation on its own. Joint is generally considered as a wide operations with one exception. We have something called broadcast joint. And what that really means is we have one small data set in the joint, and we want to cache that data set for each of the worker. So for each of the worker, there is a cache component, a caching component attached to it. So we scroll back up here in one of the slides. There's a cache for each of the workers. So just like your virtual machine, you have a cache attached to the virtual machine and the processing. So
if you had like a category of products, you
right.
can send your product table to all the workers, and then it can sum up it can do the joins. And
if you're joining with transaction, let's say, right, daily sales.
Yeah.
And so
your products and
your product will be in memory. Yeah, exactly. Your product in that case will be in memory. So there's no running around for your workers to try to grab the product name, right? If using a product ID as a foreign key or primary key there. So the performance is good because everything is in cache. No shoveling or moving data between workers are required. The next thing is sort merge. So basically the data are sorted between the two or more data sets. They have the same partition fields that's being used to sort the data. So, you just basically need to find your friend, basically find your keys and couple them together, right? There's no looking between different workers and things like that. It's very straightforward. You just need to do, quote unquote, the merge. So that's an efficient way of doing it. But most likely for general data perspective, your data is not going to be sorted in the same manner. And that's where it's the most expensive. They call that the shovel hash join. So they first need to hash your join conditions together for each of the data set, essentially sort them in this case, moving all of them into the correct order. And then you basically execute the sort merge to them in order to finish the calculations there. And that's why it's so expensive, because you're literally shoveling all the data within a partition into a correct order. So regardless of if we're reading the data, or doing the Y operation that we just talked about, we need to be mindful that Spark does break our data set up into chunks that they call partitions that we talked about earlier. So in this diagram, it's a quick way to highlight that if you choose a bad partition, or if you decide to repartition your data and you choose the bad combination, you can get this scenario where you have a lot of spikes in data in the partition, and you also have very small record counts as well. In the x-axis, I use the pickup location and then the days of the week to generate my partition. And then on the y-axis is where the record counts are. At a quick glance, we can see there's many partition above the 400,000 range. Most of the records is above 100K range, right? So there's quite a bit of them. And with the average amount of record being 59,000, which it spells problematic when you're spiking that high up and your average is so low. From a deeper analysis, we can quickly tell that there's about 20% of the partition it's above the average, the 59K. So to translate that really what it means is a fifth of the partition will take much longer to run than our average.
So the partition function you picked causes the data to be really lumpy. Some small things and some giant buckets of records.
Exactly. Okay. Yeah. The challenge is when you have so many of the partitions above the average, at the end when you finishing off your process, you might have a lot of workers staying idle while waiting for one or two partitions to finish running.
Yeah. And in this particular case, they're not just above, they're way above.
Yeah.
Like an order of magnitude bigger.
Yeah. So
is there something where Spark assigns a certain amount of space for the, I've got 59,000 records, I'm going to assign this much memory to each partition, and then the ones that are longer just take. Yeah,
so they are pretty smart about this, like adaptive partitioning that they do algorithm inside. I'm not an expert in all of the algorithm that they implement, but there's different ways of dealing with partitioning. So in our example, we're going to see there's actually only 22 partitions. Spark automatically decide for us. When I partition it this way, we have about 101 partition, I think, maybe a little more. And that was very inefficient, right? But we'll see more of that inside our demo, kind of show how things can go wrong in a hurry when partition is not quite right. And sometimes you do have to manage your partitions. When your data gets to the terabytes range, it's just not feasible for Spark to be able to handle all of that, all of the variants, right? They probably just do some kind of sampling and says, okay, this is probably the best way to handle the data, but won't be able to catch all the corner cases. Okay, so we'll jump into the demo here. We'll put our learning to the test. We're gonna start with some of the basic stuff, like reading, looking at the schema, adding columns, displaying results with limits, just really basic everyday usage things. And then we're going to jump into more of an L2 or more complex things. When we start looking at joins, we can start looking at shoveling, right? Is broadcast working? How do we get broadcast to work? How is the Windows functions going to work? And also talk about, we just talk about the repartitioning. And a lot of those items will jump into the Spark UI, which is a kind of a monitoring debugging tool that you can use to help find out what things is actually happening inside the Spark engine. That will swap over to Synapse. Okay, so this is the Synapse screen. I guess you will be here when you land. The first thing you need to do is really create a pool, Apache Spark pool. So I created two already, but I'm not going to create them. I'm just going to show you guys the configuration inside. So in here, everything that we have is memory optimized for now. There's different node sizes, basically just how many core that you need at a machine. It's important that if your data sets gets bigger, you might need a bigger machine because it takes more memory to store the data itself. Again, we want Spark likes the data to be in memory, not on disk, if possible. Do we want to do auto scaling that we talked about earlier? With auto scaling, you minimum has to have 3 nodes, so 1 driver and 2 workers, but you can scale up to 200 of them if you have them. And then
so that 481 is if you've got 3 nodes, correct?
So it's
It says estimated cost.
Oh yeah,
that's for 3 nodes.
Yeah.
But if you went with 200, you'd be way up there.
Yeah, so 481 and then 200 would be way up there, and that's, I think that number is per hour. Yeah, it's per hour number. Yeah, yeah. And then we talked about the dynamic allocation as well. So please don't default to 1 executor because you have 3 nodes. Please at least make this 2. Wouldn't work very well otherwise. And your maximum number of executor is the number of node minus 1. because the driver cannot be executed. Okay. And then the last thing I want to cover here is under the additional settings, we talked about automatically pausing. Every 15 minutes, your cluster will pause. Not going to cover too much about the Spark version, but currently the version that they have is 3.4. And I usually enable for development a session level package. So what that means is if you want to install an external package like a visualization package, you can install them as part of your notebook. Where in production, you probably don't want to do that. You want to install on a cluster yourself, so you will start up faster with that information.
So all those version numbers are based on the version of Apache Spark that you're running, correct? Because it's got Python, Java, R.
So Spark can run on many different languages. So the Spark 3.4 has some more features than the 3.3, for example. But if you run PySpark, which is what we talked about, then we know that it's running 3.10 is the language that you're using. It's good that they tell you because sometimes different version of the library, they might have different issues. And I think Python 2 is pretty much getting deprecated. I don't exactly recall. Scala is kind of a flavor of, for lack of a better way of explaining it, it's built on top of Java. So that's why their own version of that. Delta Lake is a different format or structure of data that we're going to store the data into. Something probably we'll cover in the later sessions when we talk about more designing a proper data lake, like a Delta Lake, for example. And there's certain capability that the version that it has. I think it's at 3.2 is the latest one from Databricks, but different, or even in Fabric, different services have different
So if
levels.
you change that 3.4, it will show different values.
It should, yeah.
Okay.
2.2, yeah. And I think 3.3 is getting EOL, end of life.
Yeah.
Yeah, so they want you to upgrade. And it's important to upgrade because there's some enhancements and like a lot of the adaptive optimizations that are built within the engine only exist at the newer version levels. So, but that also means you have to do more testing because of that. Yeah, so I usually enable this, and then here talk about how much cache you need. So in here, you have 50% of the memory will be used for your caching size there. Okay. So I'm not going to create mine because I already created one. And for now, I'm going to jump over. Ooh, this is not very friendly to me. So it's going to jump over to the notebook that I have. So I have two notebooks. I'll quickly go over the first one. This is how you're going to get majority of your data. So Microsoft provides open data storage that you can obtain a few different data sets, and New York taxi data is one of them. So in here, basically this is the parameter you need to update based on your own storage account and your container. And then the second block of code here, this is the open storage that Microsoft provides. So I'm just basically copying a set of data to my own environment. Now, do you have to do that? You don't. It's just easier for me to provide demos if I have a copy of data in case something happened to the connectivity, because I know I own this storage account. Okay. So yeah, if you want to run this demo yourself, please do run the demo 3-1 notebook first, so you write it to your own environment. Okay, now we're going to cover, oh, I missed one thing there. Okay, so before we start there, oh, we're actually, ooh, dangerous. That tab is right on top of of the screen there. Okay, so I'm going to run everything to save time, and we'll come back to this slide here. So we took a look at the pool itself in the configuration. We can go over to the monitor and then the Spark pool. And this will show you what is being run on this cluster. Now the cluster is starting up, obviously nothing is going to be here, but that's how you will see a lot of that information once it gets started here. So it tells you about the core that's being allocated, the memory. When they're referring to active application, from testing and development perspective, that's per notebook. So that's every notebook that you run on this pool will have their own cluster, and you will have their own application. Okay. Yeah, so you can see I've been doing some testing and things being allocated, and things being ended. So yeah, right now there's not much. Things are standing up. It will take some time for them to load up there. Okay. So I'm trying to see if I can tap back. Perfect. All right. So we're kind of in this waiting period where we're waiting for the clusters to start. Usually takes about 3 minutes time. We're about a minute and a half through. So I'll start kind of stepping over the code a bit and then come back to look at the dynamic settings at the end there. Okay, so it's important that for you to build your code initially to define parameters. More specifically, when you know things is going to change when you start running your day-to-day process. So to do that, you simply go into your cell, click on the ellipsis, and it says toggle parameter cell. And that basically makes this cell into a parameter. This looks much different than, let's say, in Databricks, or if you run Anaconda yourself, or I forgot the name of that, the IPython widget. It doesn't show the actual little text box that's above or below your notebook. It's simply just, this is just code. There's no fancy display there, except if you start doing things like leading a slider and things like that they might have a little more visualizations for you. But this probably will cover 90% of your use cases there. And the next thing we'll do is we want to make sure those variables is applied correctly. So I just do a quick print on the result, which basically tells me this is from the demo account on the demo container with the storage account name that I own, right? And of course yours will be different than mine, so feel free to update those two items. Okay, 3 minutes is almost up, and we're still waiting. Microsoft is not happy with me today. Now, going on to the reading of the file. So normally when we read the data, Synapse and any Spark prefer a format called Parquet. We'll dive into what Delta is later on in a different session, but a Parquet file basically it's a columnized, the data is coming back, the columnized compression of the data. So similar to like a lot of the SQL warehouse that you guys run on premise, it is not a row-based compression, it's a column-based compression.
What, a column store?
Yeah, it's a column store, exactly, yeah. So that's how they effectively reduces the size of the Parquet file and make it more efficient. Additionally, Parquet also support, I think, 3 different type of compressions as well, and they all allow to, they don't stop the compression doesn't stop your Spark from running in parallel. Like for example, zip file, if you zip the data, you only can run on single thread or a single core, where in Parquet it doesn't restrict that. The compression is smart enough to know that they can separate them, to run in parallel. Now the data start coming back. We'll quickly just take a look here. You always want to double check to make sure your variable comes through. This is the data source, and we're able to read the data. So display basically shows the data in the table, pretty straightforward. We don't ever want to do a display without a limit, except if you know there's only going to be like 10 records, right? Or 100 records. But in this case, I just want to limit it to 10 for easy display, kind of get a sense of what the data is. I think we dived very deep into this last time with the data analysis, so we refer you to go through that in more detail. So Parquet is relatively simple. The schema is also embedded into the Parquet itself, so we don't have to deal with the different types and variations of data coming in. Now, the second file that I read in is the CSV file, and this is the payment type. I have instructions on the GitHub in terms of how to where to obtain this data set. So this is basically the reference data, or like the product data that you mentioned, Brent, earlier. And you have to, in CSV files, you have to define your own structure, or you might get funky schema coming in. Now you can let Spark to say, hey, infer my schema for me. They might get it right, they might get it wrong. There's no guarantee. So in this case, I try to highlight that you can define your own schema for your data set for ease of definition there. So in this case, in the above command here, we just go .load, and then we pass in the format as Parquet. So that's one way of calling Spark, or this is the Spark context, calling Spark to do that. Another way to do it is Spark.read, and then you pass in .csv or .parquet. So that you can chain your command that way as well. That works. And some of the, that's another way of doing it. So if you need to pass in your schema, is read your schema, your CSV, and you pass in your do you have a header for this data set or not. The slash there is to break up your lines into, your commands into multiple lines, just to keep things easier to read. Some other configuration that you might have is, you might have a different quoting structure. If you have the escape certain character, escape character as well. There's a whole whack load of 20, 30 different configurations and options that you can apply. I won't be able to cover all of them here, but yeah, feel free to Google PySpark read CSV file options, and you'll come up with a big list of them. So in this case, I do know my list is small, so I just went to display, and those are the 6 items that we have. Okay, data type that we covered last time. I'm just going to fly through that one really quickly, as we're kind of running out of time. We can see the different types of data that's coming in from the Parquet file, the taxi data itself. If you need to fix any columns, you can easily do that in here. Again, that's a narrow operation when you try to create different columns. So all I'm doing is fixing some of the schemas, right? Like it's a int instead of a string that we have earlier. I want to calculate the day of the week using the datetime itself. Yeah, so you can also just extract like hours and things like that into the data. And so for me, instead of trying to display every single data, I just want to show what Tuesday looks like. So since day of the week starts on Sunday, Sunday is equals to 1, Tuesday is 3, and I just select a few columns to display. As you can see, this is ran in less than 2 seconds, so that's relatively quick, right, on this data set. And we have a whole year's worth of 2018 data. So there's quite a number of records in here.
Millions of trips.
But millions of trips in here, yeah. Actually, yeah, I didn't actually do a count on.
Just do a display with no limit.
No, it's gonna get really slow because it has the cache in the browser. Okay, so let's jump into join really quickly. Join, very simple, very similar to how your SQL would, right? You have a source, target, or your join, select from, join your table. You pass in the join condition that you have, and you tell it how to join. In this case, it's a unit join, so just like a regular join that you will have, right? And we'll quickly take a look at this in the Spark UI quickly. Okay, so might need 10 minutes to get to the end of this demo here. So this is Spark UI. Won't go through every single tab on the top, but essentially when you run a block of code, it's submitted as a job. Job has multiple stages. Stages give you tasks. So in this case, this only has one task. If you go into the stage, it will only tell you that there's only one stage. But what we're really, really interested in this case, that what I'm trying to show you, is the associated SQL query. And this shows you how your query or that block of code is being ran. Okay, so you scan the CSV, you scan the Parquet, like what we experienced earlier, and we filter some data. We added a few rows in here, but what we see is a broadcast exchange. So that means the smaller data set is being broadcast to join with the Parquet file, which happens to be the actual taxi data, right? Which makes sense because you only have like 10 rows in your payment type table. And you would join this data together and then you will combine them, collect them, which basically combining all the data together back into one data set, and then sends it off as a result coming back out. So we can see that broadcast is being used here. Now, looking back at our code, we never actually call broadcast. Now, this is something in their documentation. They say, hey, you don't always have to specify broadcast. The engine might detect that, but you cannot guarantee that you will do it for you. And in order to guarantee to do it for you, you would use a command called broadcast itself. So that tells the engine that this is the smaller data set for sure, and you can feel free to add that in. Okay.
So in this case, there's credit and cash, or maybe some kind of card is, so it's just
credit card.
Just a handful of things. Oh yeah, six things in your payment type.
Yeah, exactly.
So it would be really unexpected, but at some point you'd have hundreds or thousands of things in the smaller table, and you might still want to ensure that it's broadcast.
And in that case, you really have to be careful how many columns you bring in. One of the optimizations you really want to do is when you're doing broadcast, even just in join in general, is you want to narrow the number of columns first, because all of them has done in memory. The more columns you have, the more memory it takes to run.
So if your lookup table is really wide and you've got a bunch of stuff you don't care about, you want to do a select on the broadcast.
Exactly. Yeah.
Lookup table.
Yeah.
Okay.
So that's usually what happens then. I think we kind of gone through more of that in detail in the analysis side. I always truncate the data down before I do the joint to avoid that kind of a problem. Now, what happens if we decide to do it the other way around? So we force the large data set to be the broadcast, which is the trip data. And what happens here, right? This is going to take a minute to run, maybe. It will fail spectacularly, which is why I commented the code out. But I want to showcase that that's how the broadcast is going to, actually faster than I thought. It's going to say it's too much. We cannot do it, right? They cannot display this data, and the cluster has failed to max row count. So you're going to scroll through and see the error, but essentially job aborted because the stage has failed. You cannot put this amount of data onto the cache. Essentially, is what they try to say. 4
gigs of RAM on your workers, and it blew that up.
Yeah, so we can actually go back here. That's a good segue there, Brent. We can see we have total 160 gig, right, across 3 machines, 2 workers. So if we divide that up, 50% of them is memory. Yeah, probably going to run out pretty quickly. You can configure that if you want to push the boundary. You can configure what the cache size is as well. But this is kind of default out of the box there. And it does scale. If you use a medium machine, you'll get more memory, of course.
So you have to go through quite a lot to actually find the error.
Yeah, the error. Well, usually scroll down to the bottom. It's the quickest way. Right there. I was just kind of quickly going through from the top, which was a mistake. Now, part 2. I really want to spend more time here, but I think we might not have too much time today. But this is where we start using window functions. And when we ran this just now, we have 2 different aggregations that's happened. So what I really want to do is highlight, I want to pick the top 10 zones by how much fare we're charging per mile based on the day of the week. So there's a lot of conditions that got stacked on top of each other. So the first thing I do is I group the data based on the location and date of the week and try to find out what is the best average fare that we have, or aggregate them based on the information. And we're doing the average for the location and data of the week. So this really tells you which zone, pickup zone, gives you, and which day of the week gives you the best fare for that day.
You want to work Tuesday afternoons in
Right.
in the restaurant district or whatever.
Exactly, yeah. Or in the morning when you're driving people to downtown to their work, right? Now, in order to then consolidate this data one more time, we need to use the window function and organize the data, partitioning by day of the week. Pick the top 10 zone that you want using the row number and the rank function of the Windows function, essentially. And that's why I filter out any data that is less than or equal to 10 because you rank from top to bottom. So if we quickly look through this, you will see two different exchange and shovel because we're actually operating with quite a bit of data set here, the data. And which one do you pick? There's 3 jobs that got ran, right? Because we did this group by, we did this, we did filter. There's a lot of things happening here, right? We also did a role change. So the easiest way to tell is which one has the most task, most things that needs to be ran, basically, right? So again, we'll click on the Spark UI again, click on the adaptive query, and we will see there are plenty of exchange and shovel taking place. So there's one shovel that takes place. This is probably for the first aggregation, right? We see a hash aggregation on the top there, and then we're taking that information and then doing another shuffle on top of it as well.
What do you get if you click on the details?
It tells you what has been shoveled around and what has been moved, the number of record that has been shoveled around.
Yeah.
So not a huge amount, right? Don't forget, this is all Spark right now optimized based on what they do. Nothing that we have interfered with at the moment.
And the size of the blue boxes corresponds to time?
Yeah. So this is like a tag, I guess, what they call it, from the chart that they have. It's through the processing time, yeah. So you go from scanning from the Parquet file, doing all of the adding the row, the transformations, shoveling data around, and then processing them to the end. Okay. So that's kind of that. Generate this information. So if you're like a manager of the taxi service, you want to kind of know what are my top 10 area I can go to, right? Essentially, that brings in the most revenue. Now, what happens if we partition the data? So originally, Spark has 26 partition. I repartitioned the data to 113 using the location ID, the pickup ID, and then the day of week. So another thing I want to note is this took 14 seconds to run, 15 seconds to run, right? If we repartition it this way, run the exact same code, I just change the variable names. Took the same second? That's weird. No, this took a little longer to run. Oh, okay. Should took a little less. Oh no, down here. Sorry, this is the partitioning that took the 23 seconds to repartition the data. Sorry, and then the runtime. That's weird because earlier I ran this, it was taking longer than 12 seconds, but this should take longer because you have more partition to go through and there's more spice in the partitions. But it's interesting that it didn't, show that as much differences. That's what happens in live queries. You don't really always get the same results back. But when we're looking at the data again, we will see the same kind of exchange and shovel happening. That takes place with the window functions and collecting the data and send it back. I guess, Spark was able to optimize some of the items today. Okay. Finally, based on the chart that we talked about earlier that we saw, this is basically, just going to configure the chart really quickly. It resets every time I run. So the chart that you guys saw earlier is basically that generated from here that shows the amount of spikes and valleys that we have in each of our data sets here. This, more concise, more data points. And finally, we're just going to write the data out into our table so that, like what you're saying earlier, Chris, we can query it through, SSMS or connecting from another SQL environment. And if we want to read this data, we don't always have to use we don't have to always connect back to the data set. You can just read the table itself. That works as well, if that's what you prefer. Those are, convenient way of doing that. And lastly, if you want to shut down your cluster, especially you're running this on a notebook, please, you have to run this command or your cluster is going to be left active. So very important to run this. I commented this out at the beginning because I don't want a cluster to shut down when I'm demoing this in a demo. So if we go back, lastly in here, into our monitor page, we can see our application is still running. Probably it's being shut down at the moment. So I'm going to quickly jump into, it died on me already. You beat me to it. Let me refresh here. Okay, so you can look at the historical server instead. I'm just going to quickly show you about some of the configurations that we have configured in the Spark instance. So mainly our focus here, oops, I don't want to do that, is we want to show the dynamic, because I collapsed it, sorry. The dynamic configuration that we specified earlier. So we specify 4 to 5 executors in this environment. So it's important to check sometimes when your cluster is not behaving like you expect. That's kind of happened to me. I started with a cluster without dynamic allocations, and then I turned it on, but it's not reflecting in the Spark configuration. And I'm like, oh, hey, why am I still only seeing 2 executor, right? So I'm like, oh, come in and check. And that's how you will see your configurations and your, Brent, you're saying about the memories and stuff like that. Those are driver memories. So there's executor information, how many cores, and things like that, all in here. So 28 gigabytes of memory for the executor itself. Yeah. So sorry for running long, but that's pretty much the presentation there. I'll quickly just summarize so we can get you guys on your way. I'll skip over this until the end there. Okay, so we learned about the Spark architecture is a distributed system with parent-child, multiple workers, minimum of 2. Executor or the worker is the one that does the actual calculation, the processing. Driver is the one that is kind of distributing the work. The feature that Synapse Spark added is the pool to allow you to do auto scaling, reduce your management of the clusters, dynamic allocation of executor to reserve the VM that are in your pool, intelligent caching to detect when your data is being used multiple times, put it in cache so you don't have to do that yourself, and you can improve your performance. We quickly touched on what is a narrow and wide operation and how does that impact your performance. Narrow is things that you can run independently for each partition. No shuffling is the important aspect. Wide is operations are usually things that require you to shuffle the data between 2 or more workers, except for broadcast join. Data shuffling between workers do slow down your data processing, and partitions with large valleys and things like that does keep some of the workers idle, which does not help us with completing our task quickly. And you should be able to see all of this code and everything else in my GitHub repository there. So yeah, feel free to go visit. And I think the last slide is thank you. And I'll take any last questions. I know we're running a little bit long. Apologize.
Cool. Thank you.
Thank you.
Yeah, that's really awesome. So in your design process, when you're taking the business functionality that you need to do, and then bang that up, modeling it into PySpark. What kind of considerations do you go through?
Well, the data analysis was a big piece that we talked about, both from a business and technical perspective. It's number one thing I would say. And then the second one is the volume of data change is going to come in. That impacts your sizing a lot, especially if you expect fluctuations of data. Depends on seasonality or things like that. That might have problems. Another approach of dealing with data processing, which we won't be covering today, would be like, do you want to do streaming data versus batch processing? Batch processing really gets hit hard when you have a fluctuation of data coming in. You might not configure your cluster sufficiently to handle the spike of volume of data.
So if you're anticipating 100 sales a day, then all of a sudden Black Friday comes along, and you should have anticipated 10,000 sales.
Yeah, your processing is going to be ground to a halt, right? Especially for things like Black Friday, where companies probably want their sales data pretty quickly and see where they need help with resources and things like that. Yeah, that's always a challenge. Where in streaming, you can actually chunk the data to what they call micro batches, so smaller bits. Okay. So your cluster can remain the same size. It just takes longer to run through all the chunks of data in this case.
What I can see is you either got to be the end user yourself, or you've got to be sat with the end user. You better have a sample that reflects real life, because what you've shown is there's so many different parameters. You can tune it this way, like this is the result I want, but do I want to spend $1,000 getting this result, or do I want to spend $5 and wait 2 days to get the result? If you're not close to your user and understanding what's going on in the background, it becomes an expensive experiment.
Well, I mean, if you want it right away, of course, it's going to charge you more than you have a night to get it right to you. It really depends on the task at hand and what kind of SLA or service level agreement that you have with your business, essentially.
And we've got a question in the chat about how different PySpark is optimized for data engineering versus data analytics tasks.
So the Spark, we're talking about the different type of clusters. So in Synapse, there's only one type, is memory optimized. In some other platform like Databricks or in Fabric, you have more options. I think in Fabric, they might have compute and memory. I don't recall exactly, but there might be more options. And in terms of how do we optimize based on data engineering tasks and data analytics, at least in Databricks perspective, where Synapse, you don't really have as much of an option because everything is memory optimized. In Databricks, you can create different type of clusters that are more compute intensive. So there's less RAM but more compute that uses a different virtual machine type that you can help you with optimizing it. The main difference between data engineering and a data analytic task is you might have 3 analysts looking at the same data set to try to figure out what to do with them. That's mostly data analytic. Data engineering task is you kind of figure out your process or what you need. You kind of need to build that process to bring the data in. So it's often more focused on joining data. You have less repeated data to being analyzed. So your caching strategy will be different as well in that sense. In data analysis, you might want to cache your data set or the intelligent caching will help you cache as much of that data set so it can be used by multiple analysts. In Databricks, where in Synapse, I think you are on different clusters. So it might be slightly a little bit different. Depends on the platform you're on. It's quite different, the optimizations.
Just to follow up with that, we do have analytics and data engineering departments. Synapse and PySpark is predominantly in our analytics department. We do not use it in our data engineering for the limitations that this provides. So once you learn these high level systems that they're good in a lot of use cases. You will run into limitations if you do a lot of complex systems. And like we run into limitations in certain departments for a lot of various use cases, but it seems to work very well in our analytics department. But our data engineering, like I said, there's a lot of hiccups if we were to use this. We're planning on continuing this in the new year. However, our data engineers usually just maintain and like I said, with any issues or anything like that. But then that's what Dan was for, most of predominantly the analytics. So there is better ways to do ETLs than using PySpark. So we're kind of looking more into those approaches where this the limitation is not in the PySpark itself, rather than the .NET core that surrounds it, the wrapper. Yeah. And like I said, that's still a little archaic because you're still wrapped around the 3.1, where that's today's technology is 10x faster. So if you're looking for more cost-effective, cheaper ways, there is more customizable approaches than this. However, like I said, if you're an analytics engineer, this is a great tool for you. But if you're looking for complex ETLs and you're on a budget, this might not be appropriate.
Definitely not. Well, I mean, it's hard to run Spark on a budget. By default, you need 3 machines. So I mean, we have
bigger ones this year that cost a lot more as well. And like I said, with like Snowflake, for example, however, the same thing applies with what you use case you what you need it for, right? So if we have 10, 15 data sources for this, because we use like APIs, blob containers, SQL servers, multiple ERP solutions. Like I said, they're kind of everywhere in various databases. When you got complex systems like that, then these higher level systems may not be for you.
Well, I mean, Spark itself isn't built to extract data for integrations. No. That was never the intent. I know company has tried to do that and are doing that. I always separate the two. I treat Spark as your powerful compute engine. How quickly can you chunk this data out? The benefit of most of the platform, even including Snowflakes, Databricks, and Fabric, and even Synapse, is they are merging the concept of the Spark and SQL together. So you create a table that it can be read by in a SQL engine. So there's no longer that everyone has to be a Spark or a Python user. You can be just a SQL user like you traditionally are, and you're able to query the same data. You might not be able to write and compute the data as quickly as a data engineer would, but from data analyst perspective, you can still do all your work in SQL. No difference in today.
And we have them all here. So, and the cool thing about having them all, you can compare them. Yeah. So
that's also pretty expensive to have them all.
Well, like I said, people got money for it. So the thing is about it, that's the cool, unique thing about where I am, because we have them all we can compare. Not a lot of companies have that luxury or advantage, because if we realize like this costs too much money, we can take other approaches and that sort of thing. Where if you're a large enterprise company, but if you get it wrong and you're not you're on a budget, you have to be careful what's the correct tool and use. And sometimes you can go in the wrong direction. Yeah. Especially because if you want to get into more orchestrations and stuff like this, this is a great tool for analytics. We use it a lot, and I'll swear by it, regardless of like the service lists and this and all that good stuff. However, like I said, the data orchestrations, and if you're doing complex with a lot of data sources, then like I said, you can run into a big high bill if you try to do it all in here. We have Fabric, we have Databricks, we have Python, we have custom applications, we have AI, we have technically everything across the board. And like I said, you can see the difference if you test each one. But like I said, if you get it wrong, then like I said, it could cost you a bundle of money.
Well, it's best of. I think they call it the best of suite versus the best of breed. So you kind of have to die on one hill or the other.
You're here in Edmonton, aren't you, Bobby?
Yes.
Would you like to do a presentation? Like we can have Wilson's way and your way, explaining all the things you're talking about.
I think Wilson's way is actually really good. It's actually really great. In the new year, sure, I don't see a problem with that.
Okay, good.
Cool, awesome.
Thank you.
Okay, thank you for everyone attending. Thanks for having me.